Okay, welcome back, everyone. So let me start off with a couple quick announcements. So we're going to send the details about how going in person is going to work next week on Piazza once we nail down the details. I think we basically have our plan in place, but we need to test some things and make sure that what we want to do is going to work smoothly. The intent, which is not finalized yet, but the intent is to have in person in Evans 10 for those of you that want to come in person, have synchronous Zoom. This technically, I think we've worked most of the details out on that. So for that hall, so I think we have to test it, but I think we're going to be able to offer that. And of course, we'll continue to have lecture recordings posted online on the website shortly after, as soon as they become available to us through Kaltura. Okay, so that's sort of the high level bit. We'll send details about that out later. Next week will be a transition period. So participation is just going to be, everyone's going to get credit. Okay, so we could just sort of tick that off as something we need to think about for next week, and we can sort of just get used to and work through any kinks in the transition together. Okay. Okay, so that's one thing. The second thing I wanted to talk about was that I apologize. Last time I did very poor time management for us in a lecture, so I ran over by quite a bit. Instead of pushing it to the start of this lecture, I decided to just record it. So if you haven't seen that note on Piazza already, just know that the recording that's linked on the website right now for last lecture has at the end of it the remainder of lecture that I recorded, but I didn't get to when we were live. Okay, so look out for that. So those are the two announcements. Okay, let's get going for today. The lecture topic that we have today is another big core foundational one in graphics. It goes by the name transforms. Okay, so we're going to talk about transforms today. Let's start with some simple examples. What do we mean by this? Let's look at a few examples of some basic transforms. Here's one, rotate transform. So a transform is an operator that acts, in this case on objects, as you can think of it. We'll call this one R45, okay? Rotate by 45 degrees. And this transform is taking this object, which is a square with a little clock face inside of it, and it's rotating that object 45 degrees counterclockwise around the origin. Okay, so rotate transform. Here's another example. Translation transform. We'll call this one T11. This translation transform is just moving this object to the right and up 1 unit in each case. Okay, that's what the 1, 1 is. Here's another example. Scale transform. S0.5, we'll call this one. Okay, this transform operator is taking this object and scaling it down in horizontal and vertical directions by a factor of 0.5. Okay. Now, of course, we could do that non-uniformly. So here's a non-uniform scale transform. We'll call it S0.5, 1.0. And it's just squashing horizontally. It's scaling by 0.5, and it's scaling by 1.0 vertically, which doesn't change the vertical characteristics of this object. Okay. Oh, good question. There's a question on, in this transform here, why does the scale transform not hold the center? So there was an object before, why didn't it scale down to the center of that object? Great question. That's going to depend on the exact definition, mathematical definition for these transforms. So hang on to that question and we'll see exactly why in just a second. Well, I'm just sort of introducing this general notion or starting to get into what we're going to think of as transforms. Okay, let me just put this up here. What are transforms? Just functions that are acting on points. That's the way I want you to think about it, okay? So for example, if I give you a point P and we apply a transform F, then the output would be F of P. It's going to move P to an output location F of P. If you sort of dissect P, let's say P existed in 3D space, okay, then P might be XYZ. You apply the transform F to it, and you can think of it like an operator, like a function, and it outputs a new 3D location, X prime, Y prime, Z prime. Okay, so that's the way you can think about transforms. Now, of course, when you apply the transform to the whole of space, in this case, I guess it would apply on 3D space, then it does this operation on every point in the space. So it's going to transform the whole space as sort of an object, in in concert. That's the spirit in which you can think of it as an operator. We'll get into the specific definitions of a lot of this in just a little bit. But why study transforms? Why does this matter? Why is it so useful, so ubiquitous in graphics? Let's look at a few examples, okay? One is, it's really useful for modeling a whole lot of stuff in graphics that we've seen all the time. It's hard to model lots and lots of objects individually, one by one by one. In graphics, once you define one, like a robot, carefully describe its 3D geometry and so on and so forth, you can instance that object, okay, by saying, hey, give me another one at this other location. You can transform that robot into a second location, a third location, a fourth location. Just do it computationally. You can, instantiate a whole sea of robots. It's also useful at the sort of individual object level. So for example, staying with this, robot character example, you can use it to pose the character. What I mean by pose the character is that, in this case, an arm forward, stepping forward maybe, or maybe the character is walking, holding a hand overhead, something like this. The exact location of all the limbs in the skeleton of this character can be described by transforms, as we'll talk about in more detail midway through this lecture, right, on each of the component pieces of the skeleton. The transforms can operate within object definitions too. Another example, very different actually, is that we can use transforms to project geometry, polygons, triangles, from 3D onto the 2D screen. I described a bit of this when we talked about rasterization and said we'd get into those details later. We're going to get into some of those details today, and then the remainder of this lecture, which will take us a little bit into Tuesday's lecture. Okay, we'll spill over into Tuesday. But we're going to get into the details of this. If we describe this geometry like a triangle mesh in 3 dimensions, for rasterization, we talked about everything in terms of the 2D locations on the screen and the frame buffer, right? The pixel grid associated with the frame buffer. So we have to go from 3D to 2D. Transforms can help us to do that projection. And of course, that projection will depend, for example, on the camera angle, right? So here you can see that as the camera is moving, even though we have the same geometry, like a dinosaur surface, the projection onto 2D triangles on the screen is changing very rapidly, not necessarily because of, or only because of changes in the dinosaur shape, but also just because of the implied camera viewing angle or camera viewing parameters. So to recap some of these examples, okay, put it together. Why study transforms? Some of the reasons: for modeling, we can define shapes. I didn't say this, but we can define the shapes in the coordinate system that's most convenient for defining that shape. For example, a character might be described around an origin that is centered inside the character. We can enable multiple copies of the same object. For example, take that character and put it in the world, but put many copies. And then we'll have to think about the coordinate system in the world, right? And the relative positions or transforms of each of those characters. So now we have a world coordinate system to consider. We can also use it for modeling to efficiently represent hierarchical scenes. We're all computer scientists, think algorithmically. So you can think about, if you define worlds down to individual characters and their skeletons, you can think of decomposing these things hierarchically, and we'll see how transforms can be used in order to help facilitate very efficient descriptions and controllable descriptions in that way. And then for viewing, okay, I said we'll have to go from world coordinates, or transform from world coordinates to camera coordinates, actually also to screen coordinates, to frame buffer coordinates. One other thing is that we'll have to do different kinds of projections as we make that kind of viewing transformations. Some can be parallel projections, so I'll show you examples of those. Others might be perspective projections that have slightly different mathematics involved with them, that generate a lot of the three-dimensionality, the visual cues three-dimensionally that we see in real scenes or realistic looking scenes. Okay, so why study transforms? Modeling, viewing, organized this way. Many other uses too, but these are the ones we'll concentrate on today and in this course. So here's a lecture outline. We're going to talk today about how to think about and use transformations. We'll look at types. I already introduced some of the major ones: rotation, translation, scaling, a few others. We'll talk about how to think about these transforms in terms of coordinate frames or in relation to coordinate systems and changing between them. We'll talk about composing multiple transformations and what's involved, the issues that come up with that we have to pay attention to there. Hierarchical transforms, as I talked about, perspective projection will be a big part of thinking and using transforms. And we'll talk, of course, about how to implement this stuff. The biggest, sort of most core idea here is that we can represent a huge collection of very useful transforms as matrices. And there'll be something sort of specific that we, sort of a mathematical bookkeeping convention or trick that we use in graphics, ends up being very convenient and useful. It's called homogeneous coordinates. And I'm going to teach you about homogeneous coordinates today too. Okay. All right, let's get going. Linear transforms, which is a really huge branch of really useful transforms. Linear transforms can be expressed exactly as matrices. Let's go back to an example I showed before, scale transform. Okay, S 0.5 shrinks this object down here. If you think about where every point in the world on the left is going in the world on the right, you can think of, again, the output being x prime, y prime as a coordinate, right? And the output of the transform here. And on the left-hand side is xy. You can write down x prime equals sx, y prime equals sy, in this case, s being 0.5. And of course, we could write that as a matrix, okay? So this is what I mean by we can write linear transforms, express them as matrices. Okay, so this kind of a diagonal matrix here, expressing that x prime equals s times x plus 0 times y, y prime equals 0 times x plus s times y. Okay, so that's what I mean. A reflection matrix, I didn't show this one before, but easy to see too, right? So if you look carefully, you can see here that this clock face is not just, moving to the left-hand side, it's actually reflecting across the y-axis in this case. Okay, so what are the coordinates here for x prime? You can look at this, I think, and convince yourself that x prime goes to negative x, or x prime equals negative x. Y prime, actually the y coordinate doesn't change, so y prime just equals y. You can write that down as a matrix too. I'll leave it as an exercise. You can look at a shear matrix. This is a linear transformation too, okay? So what's happening here? The top of the of this object is getting knocked over. All the lines are staying straight. You can write this as a linear transformation as well, expressing x prime linearly in terms of linear combinations of x and y. Same for y prime, and therefore express it as, again, a 2x2 matrix. I'll leave that as well as an exercise to do, okay? But we can generalize this, okay? Just as I was hinting there, in general, linear transforms equal matrices. This concept, can be expressed generally as x prime equals ax plus by, y prime equals cx plus dy, and we get an a, b, c, d 2x2 matrix here, okay? So this would express the complete space of 2D transforms, 2D linear transforms that we're interested in. And we could write it also sometimes, we'll see in this lecture, write it where we just call this matrix by a name, here maybe capital M. Okay, so we can also say x prime as a vector equals matrix M times vector x, input vector x. So this is the kind of notation and the kind of math that I mean. Let's look at this a little bit more and think of it in terms of coordinate systems, okay? So one thing that you can observe right away, and this will, I think, harken back to things that you will have seen in linear algebra. The columns of these matrices are really useful to think about. So for example, if we put in, or imagine putting into this general transform, this ABCD transform, if I put in a vector 1, 0 for x and y, then the output is going to be equal to AC, right? A times 1 plus B times 0, so the output's A. And then C times 1 plus D times 0 will get C. So you can see this output is just equal to the first column. And of course, if we put in 0, 1, 0 for x and y, 1 for y, we would pick out in the output the second column. So we can interpret the columns of the matrix as the x and y axes of the coordinate frame that we're transforming to. Okay, let's look at an example. Let's look at it for rotation matrix. Okay, so here we're rotating this picture, and it happens to rotate around the origin. Oh yeah, there was the question before about why when we scale, it doesn't scale around the center of the image, it scales, towards the origin. We had a question in the comments from earlier, and hopefully now it's sort of clear why, because if we define it in this way, precisely in terms of what that linear transform is doing in terms of a matrix operation, taking input XY locations to output XY locations, then, well, why does the origin stay at the same location? It's because if you put in 0, 0, right, as a vector to any 2 by 2 matrix multiplication, whatever the matrix multiplication is, you're definitely going to get 0, 0 out. Okay, so the origin for these linear transforms is always going to stay in the same place. That's also why for this rotation matrix as a linear transform, we're rotating about the origin, okay, because the origin is going to be fixed. And what can we see here? So the point that was at this location, let's say for argument's sake that the square was a unit square. Okay, so this point here is 1, 0. You can see that 1, 0 after the rotation transform ended up at this location here. And from trig, we can recall that this the coordinates of this guy are going to be cosine theta, sine theta for this position here. And if you look a little, you got to get the signs right. For this location here is going to be negative sine theta, cosine theta. So if we think in coordinate frame interpretation about what the columns of the matrix are, we can actually just read them off. Okay, so we can see that a rotation transform expressed as a 2 by 2 matrix for rotation angle theta is going to end up being cosine theta, sine theta over here. Okay, so these coordinates go right here, and these coordinates for the x and y location of that point there go into this column here. Okay, negative sine theta, cosine theta. All right. Now, actually, if you look at this one, you got to be a little careful, okay, about the signs. And I honestly I have to derive it from scratch every time after I haven't seen this for a little while. But the negative sign goes up here, okay? The negative sign doesn't go down here. And this is for like a right-hand rule convention of theta turning counterclockwise. Okay, so if you point your finger at the origin, which way does the rotation happen for theta? It goes right-hand rule would tell you it goes counterclockwise. Here's an XKCD comic that helps you remember this. If you remember the whole comic or if you look it up. So cosine 90 degrees, sine 90 degrees. Oh, the negative sign is down here. If you were paying attention there, this is the opposite negative location. So if you reason about this, this is actually a rotation of 90 degrees in the clockwise direction, right? Not counterclockwise, which looks like that, okay? 90-degree clockwise rotation. Okay. All right, XKCD. Okay, let's keep going. Translation transform. I already introduced this to the beginning, basic transform. But I think we have a problem here. I just went through and said, oh, linear transforms, huge spacer transforms, very flexible, very useful, can all be, like expressed as matrices, and all 2D transforms, linear 2D transforms at least, expressed as a 2 by 2 matrix. But not, yes, somebody noticed. That's XKCD number 184. It's 184, no kidding. Oh, love that coincidence. Anyway, T11, translation 11, right? Again, it just moves, in this case, the object up and to the right by 1 unit, each in X and Y. So easy to write down actually in equations, right? X prime equals X plus T sub X, Y prime equals Y plus T sub Y. In this case, T sub X equals 1, T sub Y equals 1. But for any non-zero txty, you can't actually represent this as a matrix, right? Can't express this as a matrix. Why? I actually said before, right, the intuition. So if you put any 0, 0 vector into a 2 by 2 matrix multiplication, you can convince yourself very rapidly that you're going to get 0, 0 out. Okay, you have to get 0, 0 out. In fact, it's one of the properties of linearity. But somehow in this transform matrix, we're taking the origin, which was at this location, and went up here, the origin moved. Okay, so this cannot be expressed as a 2 by 2 matrix. This is not a linear transform, it turns out. which might be a bit confusing. So since maybe it should be, I forget what's the definition of linearity again. Actually, I'm not going to go back over the core definitions of linearity, the axioms for something to be considered a linear transformation or a linear operator. Not that complicated though, but I expected you would have seen that in a different class. I'm just going to go through and tell you in graphics, what's the solution that people have landed on for solving this translation issue or handling this translation issue. Now, let me observe, it's not a huge problem. You could, of course, implement it yourself just by bookkeeping that says, okay, we have a 2x2 matrix for that sort of linear transform part, and then we'll just have like the transform as well. We'll keep two coordinates for X and Y translation, no problem. Of course, you could write a data structure that would do that. People had a different solution though in graphics. Let me tell you what it is. It was homogeneous coordinates. And the reason why this is really useful, we'll sort of see as we go through, as we look at 3D transforms, and then later when we look at perspective, it'll come back again. Okay, so what I'm introducing to you now will sort of seem a bit like overkill for the current problem, but let me tell you what it is. So the solution is to add, or the proposal is to add another coordinate. This does not make it a 3D transform. This is not appearing in 3D. This is still just for transforms in the plane, okay? You add a third coordinate called the W coordinate, okay? And you get something like this. So a 2D point would be X comma Y comma 1. A 2D vector would be like an X comma Y comma 0. So you can think of a point as like a location in the plane, a vector sort of being like, something with like pointing in a particular direction, a displacement, if you will. Okay, so that's the difference here. And now it turns out you can express translation as a matrix. How did that work? Let's take a look at it. Okay, so if you had given in a point, X comma Y, that's the input here to the matrix multiplication, you write it X, Y comma 1, XY1 as this column vector. And then you can write the matrix for transform now like this, okay? It has like has a identity matrix in the top 2x2. Come back to that in a second. The translation goes here, Tx, Ty. And the output gives us an X prime, Y prime, W prime. Let's crank through the math on this. It's just matrix math. It's just a 3x3 matrix multiplication now. So we get 1 times X plus 0 times Y plus Tx, X plus Tx. Okay, exactly as we wanted, and Y plus Ty for the next one. And then for the last, the homogeneous coordinate, the W coordinate, we just get 0 times X plus 0 times Y plus 1 times 1. So we get a 1 out as well. Okay, so look at this. This output is a point that's at X plus Tx, Y plus Ty. Okay, so a little bit of bookkeeping sort of magic, and we got the thing that we wanted. Why is it 1 and the 2D point, but 0 as the 2D vector? Yeah, good question. It's just a convention. And it works out, in the way that you would kind of expect it. Let me just sort of walk through that on this slide, okay? So you can do operations now on these 3-element vectors, xy1 or xy0, and it's a valid operation if that W coordinate ends up being a 1 or a 0. So for example, you could take one vector and add it to another vector. I think intuitively, if you think of a displacement and then add another displacement, you would end up with a displacement. And you can reason to yourself that if the W coordinate is a 0, then it would still be a 0 in the output. If you take one point and you subtract another point, you could say, well, maybe I want to interpret that as the displacement between the two of them. That would be a reasonable mathematical thing to do. And it's going to work out in the math. It's going to give you exactly what you want, the displacement vector pointing from the first one to the second one. And the W coordinate is going to end up being 0 if we do element by element subtraction here, just normal sort of vector math. If you take a point plus a vector, you'll get a point because the W coordinate, right, is not going to change. It's going to be 1 plus 0, so you'll still be 1. If you take one point and add it to another point and did it element-wise, you're going to end up with a W coordinate of 2. Okay, so that is a not valid operation in homogeneous coordinates for handling points and vectors. Okay. And so if you sort of think of it geometrically as well, what is a point plus, what's one position in the plane plus another position in the plane? You could define something as reasonable, but actually, if we want to talk about moving from one point to another location in space, we would use this one here, a point plus a vector. Okay, one location is place plus a displacement. So this is sort of what's worked up in this kind of a space. But the primary use case that I described earlier was to handle translation. There'll be other uses that we'll come back and talk about later. And so in general, for what's called an affine map. An affine map or affine transform is composed of a linear transform plus a translation. So we have x prime plus 1 y prime equal to this ABCD matrix times the input xy plus a translation vector. We can collapse all of it now down to, using homogeneous coordinates, one 3x3 matrix that can represent an arbitrary translation and linear map all in one. And it's going to be of this form: ABCD in the top left, TXTY translation here, and 0, 0, 1 in the bottom row of this matrix. Thanks for the questions. Yeah. I talked about some of these. I think maybe I answered some of these, maybe not all of them. I'm going to keep moving though. Maybe Rishi can help to answer some of these. And if anything comes up that's not resolved, then raise it up and we can talk about it. Anyway, let me wrap up this discussion about 2D transforms by just summarizing the key stuff I just talked about. Okay, there's a scale transform, rotation transform, translation transform. The scale transform with 3x3 matrix notation is going to look like this: SX, SY. Okay, there's no translation. Rotation, we have the cosine alpha, sine alpha, negative sine alpha, cosine alpha. Remember where the negative is. 0, 0 here, no translation. For translation, you have 1, 1 up here. Okay, unit or identity 2x2 transform, and the TXTY at this location. So that's the way that all these transforms roll out that I described. Okay. There's some names that are often given to these. This is just naming. It helps a little bit intuitively. It comes up a little bit more in things like, it comes up, and especially in things like computer vision, some of this stuff ends up being kind of conceptually important. I'll just tell you what some of these names are. This rotation translation, we can think of it as rigid body transforms. Okay, I think that's pretty intuitive because it's sort of like if you applied this transform, you would take an object and you could rotate it or you could translate it, but you can't change its size or its shape in any way. If you include scaling in here, this is a broader set of transforms, right? It's a superset that's sometimes called similarity transforms. And the superset of that could be something called affine transforms, as I described. That would be like an AX plus B. Geometrically, you can think of this. Euclidean is another name for rigid body transform. Okay, so only things like translations or rotations in the plane. So you take an object as if it's rigid and you can only do those kind of movements to it. Similarity means you can scale it up, scale it down. You can stretch it uniformly. And in particular, the intuition is that the similarity transform doesn't change the underlying shape of the object. Whereas like for the affine transform, now you can also do things like shears. You can do things like stretches that are not the same in both dimensions. And so these would change the shape of the object that you're looking at. Okay. What is an example of a non-affine transform? A good question. One example that we'll look at, there's lots. It's anything that doesn't meet the form of this AX plus B, where X is the vector, A is a 2x2 matrix, and B is a column vector. Okay, so anything that doesn't fit that form, lots of nonlinear versions. We're going to look at one later that's very important in viewing. It's the perspective projection matrix. Okay, so in this lecture, which we might get to on Tuesday, you'll see a very important version of something that's not affine. For completeness, let me just observe there's also an inverse transform. Okay, so if you have a transform M, there's the M inverse transform. And this is, if it exists, if you don't have a degenerate transform, the versions that we've talked up to at this point are all non-degenerate, then this inverse will exist in both the transform operator sense geometrically that we've looked at by reversing the transformation geometrically that we're looking at, and will also exist mathematically in terms of the 3x3 matrix as its literal mathematical inverse. Okay, so geometrically, what I mean, if M does this, okay, it takes this clock face here and it moves it over and rotates it, then M inverse is going to do the opposite. It's going to take something that looks like this and it's going to return it to this this original location here. Okay, and the matrix, as I said, is going to be the literal 3x3 inverse matrix for M. That was already a segue, that picture I showed you last time. I want to dig into that a little bit more, composing transforms. So mathematically, this is all about commutativity. Okay. And so the punchline is that, okay, you got to be careful because these matrices are not commutative. Easy to say, I'm sure you've seen this before this commutative issue and thought about this for matrices most likely before. If you haven't, you can look at it here. We're going to go over it. But I guarantee you that when you start using transforms, the ordering of the transforms, both whether it's from right to left or left to right, and then which order they appear in, is it ABC or CBA? like all of these things are very natural places to get tripped up. I don't think I know a single person that's tried to practice, write code in practice with any of these things that hasn't hit these kind of issues. So let's just take a look at some examples that you're likely to encounter in debugging land. What was this transform exactly that I showed you before? Okay, here's the input, here's the output. This is transform M, but what is it in terms of, let's say, decompose into basic transforms? Translate, then rotate, maybe? I mean, clearly it looks like there was some translation and rotation, right? But if we translate, let's say we translate it over 1, 0, and then we try to rotate it, wait, what happened there? It ends up way over here. So if we apply, logically speaking, T10, and then we apply R45, which, by the way, we would write in matrix form this way, right? T10 is a matrix multiplication on XY. So the output of that would then be multiplied by R45, which would be the second 3x3 matrix. We have to write it from right to left. So that's one thing to note. But if we do it in this order, it wasn't the actual transform that we were trying to accomplish. You can see it ended up in the wrong place. Okay, you can persuade yourself this is where, that if you took this and then apply R45 to it, remember, counterclockwise rather, 45 degrees around the origin, it's going to end up over here. So this was not the right choice. Let's try rotate, then translate. Okay, so we rotate R45 and then translate, ends up over here, which if you may have forgotten the picture I showed you earlier, but this was the one that I was trying to accomplish. The high level bit here is that, look, transform ordering totally matters, right? Okay, T10 and then R45 is not the same as R45 then T10. Is graphics land based in degrees and not radians? No, not at all. It's based in angles. Okay, so whether you want to choose degrees or radians as units for your angles is totally up to you, and I'll use them interchangeably, but always make the context clear. So transform ordering totally matters. It's for a simple fact that matrix multiplication is not commutative, right? Which is a basic property. And I'll just write it down explicitly. Okay, so recall the matrix math represented by those symbols. So this is R45 here. This is T10. Okay, 10 being located in the translation slot over here. And we're just saying that if we do one versus the other, these two matrix multiplications are not the same. And if you wrote them all out and cranked the math, you would find that's absolutely the case. And I mentioned already, I'll emphasize again, note the matrices are applied from right to left, and we will write it even when we write it in operator form, we're going to write it from right to left, because if we don't, that will be the wrong ordering of application onto some kind of vector on the right-hand side. Okay, so this thing over here, the reason that it's written right to left is because if we put in the column vector by convention on the right-hand side and apply these matrices by multiplying on the matrix on the left-hand side, then we have to write it in right to left order. This is the reason. If we have a whole sequence of these affine transforms, examples we already looked at, then we compose them by matrix multiplication. I just want to observe, this is really important for performance. Okay, I haven't really gotten into computational issues yet, and I'm not going to get into them deeply here yet, but I just want to observe at this juncture, right? This is a really significant mathematical fact, and it's very significant algorithmically. So in particular, if we have like a scene with a whole bunch of vertexes in them, describing a very fine polygon mesh, for example, a triangle mesh, and then we say, okay, I want to take that dinosaur mesh, and then I want to just do all the things I've been talking about. I want to translate it, then I want to rotate it, then I want to scale it down, then I want to put it into this world with this sort of camera transform next to this tree, blah, blah, blah. Well, if I have 5 or 6 transforms there, and I apply them literally one at a time to every vertex, then I have to do many, many, many matrix vector multiplications, one after the other for every vertex. But that's, of course, not what we would do at all. And no one in graphics will do that. Instead, what you would do is you just take the matrices that represent the transform and you would calculate the net transform, right? The aggregate composed transform just by multiplying A1, A2, A3 in the correct sequence altogether. Each of those is a 3x3 matrix. So you end up with just one 3x3 matrix at the end that does all the work in one. And then you only need to do one 3x3 matrix vector multiplication for every vertex in the scene. Okay, that's going to be way, way more computationally efficient. This just summarizes the math of what I was saying. Okay, apply all of these in sequence to xy1. Yeah, you could, mechanically one by one. But if you have a whole bunch of vectors, you would pre-multiply all of these so that you can use that pre-multiply matrix for each vector in turn. Let me do an example of decomposing complex transforms. In general, you might not be given the sequence of things that you want to put together. You might be given a net transform and sort of try to reason about how am I going to decompose that back into some things that I can reason about for implementation purposes, or just to understand sort of what is going into any particular complex transform that you're seeing. Let me give you one example, okay? How do we rotate around a given point C? So let's say we had the clock face, but let's say it was not located at the origin this time. It was up here. How do I rotate about its bottom left corner as an example? Yeah, that's right. Translate to the origin, rotate, then translate back. Okay, this would be a way to apply the basic transforms that we've talked about. And it'd be a way to sort of calculate it. You can try to calculate the transform for this matrix from scratch. Actually, it's not trivial, can be done. I can talk a bit about that later as well when we look at coordinate frame transforms. But here's a way to reason about it based on what we've just looked at. We can have translate negative C, if C is the coordinate of this corner here. T negative C would bring that corner to the origin. We can then apply R alpha, and then we can apply TC to put it back over here. Okay, so this would accomplish this rotation. And the matrix representation, of course, is right to left. Okay, so the first one we put as T negative C, goes over there, then R of alpha, then T of C. Ordering matters. One more thing before we leave 2D land, coordinate systems. Okay, I want to share with you how to think about coordinate systems. This is a really, really useful way to look at transforms. It also, at least personally, I always found it to involve a little bit of sort of like visualization or conceptual gymnastics that I often got kind of inverted or going the wrong way. So I'll try to describe it to you as clearly as I can. And then if it's perfectly intuitive to you, great. If you're a bit like me, it's like, it seems a bit slippery, just spend a bit of time with it later. And I think it'll become very familiar and useful to you. What am I talking about? Many times we want to change, or it's very convenient to change from one coordinate system to another one. Let me give you a simple example. Let's say I have a dinosaur and I'm going to describe that object in its own coordinate system, okay? Maybe in centimeters. So I have a dinosaur on my desk. I'm going to try to measure it or scan it. And I'm going to say, I'll pick an origin. I don't know, I'll pick it right in the tip of its nose, for example, okay? For convenience, I'll make that the origin. I'll just describe the dinosaur nicely centered against the axes in that coordinate system. Great, so I got that. Then a couple of years later, I got the same model and I said, hey, I want to put it into some 3D world I'm going to render. And I want it to be big, like the size of a tree. And I have this world, it's got buildings in it, it's got trees in it, and they're all described in meters. So now I've got to position the dinosaur in the 3D world, and I have to sort of scale it up appropriately from centimeters to meters or whatever, okay? I have a coordinate frame for my dinosaur. I have a coordinate frame for my world. I need to transform between them. That's an example of the kind of thing that might come up. I wrote a slightly more general version of it, or drew it here. Okay, let's say we have X, Y. Let's say think of that as world coordinates. And let's say we have the coordinate system for something, okay, that we want to transform into world coordinates. So we can describe this coordinate frame by 3 vectors. We can describe by O, U, and V, O for origin. So we can describe the XY location of the origin of this coordinate system. We can describe this vector U as its XY displacement coordinates. And we can describe this vector V in terms of its XY displacement coordinates. Okay, in fact, I've written OUV here, like implying that what units are those, or what coordinate system? I'm describing them to you in X and Y. Okay, now given coordinates in this OUV reference frame, the question is, what is the transform to coordinates in the XY frame? Yeah, it's very like a change of basis. It's very like a change of basis. Okay. Now, it's a bit tricky because in this case, we're talking about 3x3 transforms. These are not linear transforms, right? They're affine transforms, so it's a translation component, but it turns out it's going to work fine. Okay, let's just work it through and see how it pans out. So what I mean by this exactly is, okay, so, okay, sorry, I was saying, okay, here it is. We can look at this transform F. And the transform F is just going to be written in this form. We just take the UV0, UVO rather, and we put them into a matrix eventually to create a 3x3 matrix in this form. So specifically, the coordinates of U are UX, UY. So literally, the coordinates of that U displacement in the XY units. Same for VX, VY, and same for OX, OY. And we end up with a 3x3 matrix. You can convince yourself that this is the right matrix to take us from, but you should actually do this, okay, to take us from any coordinates that we provide in the OUV coordinate system into the XY coordinate frame. Let's look at a simple one. Okay, so let's say that we take the origin given to us in OUV coordinate frame. That would be like 0, 0, 0 here. Okay, if we multiply by this, what are we going to get? We're going to get popping out the OX, OY. Oh, sorry, 001 rather. It has to be 001 to be a point in that space. Okay, we'll get OX, OY popping out, which is exactly right, because if I gave you the origin in OUV coordinate system and asked you what are the coordinates in XY, the coordinate's going to be OX, OY, okay? Similarly, for any point that I give you in the coordinate frame OUV, applying this transform is going to give it to you in the XY coordinate system, XY coordinates. So this is really nice. It's very simple, very easy to remember once you do. And once you convince yourself that this is giving you the right answer, then, very nice to apply going forward. It gives you a way to read off the columns of the matrix if you're given the coordinate system that you care about. Let's look at an example here. Okay, so let's say we have, this is like analogous to the dinosaur I was saying. I've modeled some object. In this case, it's a letter R in its own very simple coordinate system. See, I put it in a box and I made it a unit box here. And I put it right side up, okay? Similar to the dinosaur I was describing before. Convenient coordinate system for me to define the object that I'm modeling. Later, I'm like, hey, you know what? That object, I wanted to be in some special world. It turns out that it was kind of on, I don't know, the face of a cube. It was tumbling upside down. It happened to look like this. How do I go from all the positions in this R object over here to their positions in XY? That would be the nature of this kind of transform. And using the methodology I described before, we can do it just by looking at the 3 key coordinates. You can look at sort of what happens to the origin. The origin goes to 1, 1. As you can see here. You can look at what happens to a vector that's aligned with the x-axis over here. So this vector here, where does it go? It comes here. What's the coordinates of this vector here? I annotated here. This is unit length, okay? So this thing, you can visit yourself as square root of 2 over 2, square root of 2 over 2. What about the y-axis? It went down over here, okay? The coordinates of this vector here are 0, negative 2. So if we take all of this, what I was trying to explain on the previous slide is that you just write it into a coordinate frame transform like this. The transform T here, it looks like this. You put the you put the U transform, this x-axis went where? It went here. So square root 2 over 2, square root of 2 over 2 goes here. This blue vector here went to 0, negative 2. And the origin, that's the O vector, right? It goes to 1, 1. So you can read off the columns of this T matrix in this way. Yeah, this is good intuition in the comments. You can think of the U and the V as basis vectors. That's a very useful intuition that you can think about it for the coordinate frame that you're looking to transform into the world frame. And if they're not unit transformations, then that absolutely implies scaling. As you can see here, okay, so this R, you can see it's vertically stretched after this T transform. And why? Because this, or how can we see this? Because that V-axis over here, by the blue arrow, went to 0, -2, which is twice the length, and you can see it's stretched. Let me just observe there are two interpretations of a transform that you can build from this. Okay, so if I give you a sequence of transforms, I've actually been describing it to you a lot narratively already this way. You can think of it as, say, here I start with a little house, say, I'm going to translate the house down into the left, I'm going to scale the house down, then I'm going to rotate the house, okay, counterclockwise, and then I'm going to translate the house up and to the right. Makes perfect sense, right, narratively. A totally symmetric, and by the way, that's a really useful way to think about modeling transforms a lot for you. And I imagine that you'll do a lot of these if you, in the assignments that come up, or if you do a final project that involves any amount of world modeling. If you have models or objects that you're intending to put there, you'll do this kind of thinking, okay, one by one. And then we talked about you just take these transforms and you put them, write them down right to left, and you can do matrix multiplication on them. Everything will work out. I just want to say that there's another way that's very common to think about exactly the same set of transformations, and that's to think of it in terms of what's happening to the coordinate frame. So interpretation 2 is transforms on coordinate systems. Start again with the house here. What we can actually think of is that we can think about moving the coordinate frame. Maybe a little mind trick is worth here. Why don't you think with me about this coordinate frame as sort of like a camera. Okay, we're positioned in the camera. We're going to move that coordinate frame of the camera to the house. Then we're going to sort of zoom out. Okay, so we sort of scale up the size of this, scale the field of view of this camera. We can rotate the camera's viewpoint, and then we can translate the camera's viewpoint. Now, the pictures are different from the top and bottom that I drew, but I think you can see that the net result of it is the same, actually, right? It's the same transform. We've just been interpreting it in different ways because the relative position and size of this house at the end here is the same relative to the coordinate system, okay? So actually this represents, if you wrote down all the matrices here, it's going to be exactly the same set of transforms. Actually, they're inverses when you apply them in a camera sense, okay? But it's exactly the same final result that we're going for, except that we're interpreting it as transforms on coordinate system versus transforms on the object points themselves. Okay, so that's 2D transforms and what I want to say about them actually. Now let's go to 3D, okay? The good news in 3D is that a lot of stuff just comes for free. Some does not though, so we'll get more into that. So 3D transforms, we can use this homogeneous coordinate again. So instead of xy1 we had before, now we have xyz1 for points and xyz0 for vectors. All the transforms we'll be looking at, the affine transforms will be represented by 4x4 matrices, not 3x3 matrices, okay? And in particular, scale looks like this. It's a diagonal matrix in this top 3x3 part here. So if it's a non-linear, a non-uniform rather scale, Sx, Sy, Sc, it looks like that diagonal matrix on the top left. Translation ends up the same, Tx, Ty, Tz, analogously to 2D case, very simple. The coordinate frame transform that I talked about earlier just goes exactly the same, okay? You just have a third coordinate, third basis vector, if you want to interpret it this way. So U, V, W, and O. Really nice. 3D transforms are fundamentally more complicated, though, than 2D transforms, actually. I guess I spent a bit of time talking about this and get a little intro to this. This is actually a pretty deep mathematical topic. People have lots and lots of ways to try to represent 3D rotations and sort of, compose them, interpolate between them, lots of stuff. I'm going to give you an intro to just a couple of these. I don't need to or want to go too deeply into that topic in this course or belabor the math on that. I want to give you sort of a flavor for this, okay? The thing that gets more complicated in 3D is that we have to talk about what we're rotating around. In the 2D case, we, by convention, rotate around the origin only. Okay, and we have a right-hand rule. We have to have a convention for whether we're going clockwise or counterclockwise. That's just the sign of the rotation angle. But in 3D, we have to say actually the axis over which we're going to rotate space. Okay, and that is just fundamentally more complex mathematically. If we rotate around the x-axis as an example, so this is r sub x of alpha, then this turns out to be the matrix formulation of it. Okay, so it's cosine alpha, sine alpha, negative sine alpha, cosine alpha. It ends up here around these units, around these elements of the matrix here. They're similar for r sub y. They spread out like this, and r sub z ends up over here. Good exercise to go and convince yourself that the signs of all of these things are in the right place. Not that you need to memorize this in any way, but I think it's a useful exercise. It doesn't take long to go through and just sort of try to put in some test points and convince yourself that this thing is, that these matrices are doing the right thing for rotating around the x-axis, right-hand rule, around the y-axis, right-hand rule, and around the z-axis, right-hand rule. They're all counterclockwise counterclockwise from a perspective, from a right-hand rule perspective, okay? And it turns out you can represent any 3D rotation, not just around the X, Y, or Z axes. You can rotate, express any 3D rotation in terms of Rx, Ry, and Rz. So Rxyz with alpha, beta, gamma, this can let you, represent a lot of things very usefully. There's so-called Euler angles for rotation, and they're very common. They're often used in flight simulators, for example, as the roll, the pitch, and the yaw. So if you've never seen what those are before, if you're in an airplane and, one of the wings is going down versus the other, that's called a roll. The pitch is like, oh, you're about to take off. The nose lifts up, it pitches backwards. Okay, that's the pitch angle, and the yaw is, the other one there, as shown in that diagram. Okay, sort of the nose is pointing to the left or the right, or rotating towards the left or the right. Okay, so roll, pitch, yaw, very common, very useful also. I do my slides there. Okay, that's fine. There's another way to construct. And this is the sort of thing about how to express 3D rotations. If I give you a 3D rotation, can you sort of decompose it into the Euler angles? You can. There are other ways to sort of express the rotation sort of directly. Actually, we can go by analogy to what we described earlier in the 2D case. Can we rotate about a point C, right? We went through that example. We can do a similar thing here, but it gets a little bit more complicated to compose all of these. Let me just walk you through it, okay? Let's say that we have an axis here. We want to rotate, say, around, how did I set this up? P-U-V-W, sorry, okay, rotating around W. Okay, we're rotating around this W axis. And so how do we express that? One way is that we can imagine rotating that W axis until it aligns with one of the coordinate axes, and then applying one of the basic 3D rotation transforms that I showed you earlier that are easy to write down, and then rotating all the way back to put the W axis where it was originally. Okay, so that's sort of a way to decompose this general 3D transform, a general 3D rotation. So we applied the transform that looks like this, F inverse, then R sub Z of theta, then F, by rotating the W axis that's shown here until it aligns with the Z axis. How do you do that though? We can write down that change as a coordinate frame transform. Okay, what I was calling F in some of the earlier slides. And we have to choose the rotation, to choose the coordinate frame axis. Okay, so let's reason that through. We can construct an orthonormal frame transformation, F, or coordinate frame transform, where we say the origins keep it in the same spot. Okay, P is at the origin. Yeah, well, actually, P can be general too. P can be floating out in space if we wish. And then UVW, where W is the vector that we want to rotate around. And then we pick two arbitrary vectors U and V that are just orthogonal to W. Okay, so they have to lie in a plane U and V orthogonal to W, but then after that, we can choose it arbitrarily. So you can construct an F transformation matrix of that kind and then apply as shown here. Okay, so as I said, move to the Z-axis, rotate, then move back. So that's one way to sort of construct it by analogy to what we showed before. Here's another sort of cute trick, okay? Some magic formula. It's called Rodriguez rotation formula. I'm not going to test you on this, but it's very useful to know, so I want to at least just show it to you, okay? Rotation by angle alpha around an arbitrary axis n. That's what I called W on the previous slide. Okay, wow, look at this. It's just a closed form expression with, you can just write it down for a matrix, okay? Eventually you get a matrix R, a 4x4 matrix that represents this rotation around an arbitrary angle, by an arbitrary angle around an axis n. No kidding, very useful. So I present it to you here. How to prove this magic formula? Maybe we can take this offline and sort of look at it in the comments if you folks are interesting. It's correct. If you want to convince yourself of it, not a bad exercise to practice some of this kind of matrix, vector sort of math, this kind of thing. Not a bad practice exercise. I'll sort of sketch it very, very quickly, and then I'll move on to other topics I want to share with you today. This matrix N over here, you can convince yourself, but you have to do a little bit of work to convince yourself. You can convince yourself that matrix N actually computes a cross product. That is, if I give you a vector X in, okay, XYZ, vector X, then if I apply this matrix N to that X, I will actually compute little n. What's little n again? Little n is the axis, the vector that we want to rotate around, okay? Little n cross X. That's kind of useful. Might use it somewhere else, potentially. Might be useful to you. It's a matrix formulation for cross product by vector n. And then after that, you could assume an orthonormal system where you take that vector n again, and then you come up with two arbitrary vectors, E1, E2, arbitrary, except that they have to be orthogonal to n, okay? And orthogonal to each other. So in the plane that is perpendicular to n. And then you could write down a whole bunch of things. You could apply R, this matrix R, to each of these vectors in turn, to n, to E1, E2, and see what happens. And if you do this, then I think you can convince yourself or prove to yourself that this Rodriguez rotation formula is working. If we apply Rodriguez rotation formula, the axis n has to pass through the origin, correct? It does. It does. Okay, so a couple of high-level things about rotation in 3D. There's a lot of other stuff on rotations in 3Ds that may be interesting to you, may be useful in some projects if you have them. Quaternions, I'll mention, is one representation for them that is sort of a generalization or related to a generalization of complex numbers. Exponential maps is another one. There's sort of different properties when you try to interpolate them that can be useful in certain kinds of applications. But that's the last thing I want to say about 3D transforms and how they generalize from 2D. The next thing I want to talk to you about are hierarchical transforms. Okay, and this one's a lot more conceptual. I don't think the concept's very hard, but I want to walk through an example so we can see something visually together to sort of anchor, how useful and how, common this is. Okay, let's just compare modeling a simple little character here using a hierarchical transform, representation versus a non-hierarchical representation. Non-hierarchical in this case, I'll call linear. Linear just means a list, okay? Not linear in a linear system sense. Linear as a non-hierarchical. So what am I trying to say? Here's a very simple character, as you can see on the right-hand side. You can see it's just composed of little rectangles, okay? So you can sort of think of it as taking a unit square and then trying to figure out how to, scale each of those unit squares and then rotate them and translate them to the right kind of location. There's a head, as you can see here, a torso, parts of an arm. You could just store it as a list of elements of the body and store a transform, one associated with each one of these, right? Clearly, you can make this work to draw the character on the right-hand side. That'd be fine for a lot of applications. So each shape will be associated with its own transform, but there's some drawbacks that happen right away. Let me give you one example. a single edit on this character. So I mean an edit in a semantic sense. Okay, what's an edit? Like maybe I want to make the character raise their whole arm up. Okay, raise the whole arm up. A sort of simple edit, a single edit conceptually, that could require updating a whole bunch of transforms, right? Because now I got the upper arm, middle arm, and the hand. Upper arm rather, lower arm, and the hand, and I got to update all of the transforms for each of those, and I have to make sure that they all stay consistent. More generally, if I just want to move the whole object somewhere else, then I have to change the transforms for each of these, elements, all of them one by one. That's another thing that happens. Let's look instead at the hierarchical representation. Okay. So in the hierarchical representation, what we do is we say, well, let's start with the torso. Okay, so if you tell me anchor ourselves on the torso, we can describe the position of the head relative to the torso, then the right arm or the relative to the torso, and the right arm is composed of pieces that I can describe the position of the upper arm, the lower arm, maybe with rotation, and the hand maybe with rotation relative to the other parts of the arm, but all relative to the base location of the right arm. Similarly for the left arm, the right leg, and the left leg. That's the idea. Okay, so just a simple hierarchical breakdown. This, of course, at least in the case of this character, is going to end up with a grouped representation. It's going to be a tree kind of structure. Each group can contain subgroups, kind of as I showed there, okay, in that case, and for the skeleton. And each group, in this case, is the thing that's associated with a transform. There are fewer transforms here than in the list representation that I showed, okay? Each group in this hierarchical representation is the thing that has the transform associated with it. And the transform on any leaf node shape, which may be a subgroup of a subgroup, right, of a subgroup, the transform on the leaf node is going to be the concatenation of all the transforms on the path from the root node down to the leaf. Maybe that's obvious, what I just said, or maybe something that happened that was a little bit not where you expected me to go. Let me say that again. The transform on any leaf node shape is going to be the concatenation of all the transforms going from the root node down to the leaf, okay? I'm going to show you an example of that back on that character in a second, very explicitly, okay? Just to really anchor all of that in visually. But maybe make an observation at a high level first. If we change one of the group's transforms, then we can affect all the parts that come down from it. For example, if I translated the torso, in this case, then the whole object moves. I only need to change the transform on the torso, right? And everything will come along with it. If I change the transform on the arm, for example, all the upper arm, the lower arm, and the hand are all going to come along with it. So this allows high-level editing by changing only one node, and which node it is going to be semantically set up in a way that is, if we design it properly, in a very natural kind of a way. I said that. Let's take a look at this, okay? I'm going to do some pseudo code here. This is actually pretty similar to code that's common in graphics, believe it or not. And so I'll just show it to you with some of the idioms that are involved. So let's pretend we're going to write some code to draw this character, and we're going to do it in this hierarchical transforms kind of representation. We're going to leverage that representation. So we can start by say, okay, translate 0, 10, up and 10, and I'm going to draw the torso. Okay, so in this case, draw torso, draws a little purple box. Great. Now, the way in which the head becomes relative to the torso, you can see right away by this block of code. We're going to push a matrix, and then sometime later, we're going to pop a matrix. This pseudocode just means literally we have a data structure that's a stack, okay? And we're going to push the current matrix onto the stack. And when we do that, we're actually going to push a copy of it onto the stack and keep the current copy on top. Stack, first in, first out. So later, when we pop the matrix, all we do is we take the current thing that's on the matrix, on the top of the stack rather, throw it away, and we pop back up to the one before, to the copy that we made before. Okay, so that's what this push pop does. This translate 0, 5 here doesn't set the transform to 0, 5 translation. What it does is it concatenates onto the current transform at the top of the stack. Okay, so we've translated 0, 10 to get to the conceptually the center of the torso, if you will. we're going to translate 0, 5, which is relative to, we're going to, compose these transforms, right? We're going to go another 0, 5 up to get to the head. Then we have a rotate head rotation angle, okay, to tilt it, and then we draw the head. Okay, so you see what happened there? There's some good questions about this, applying the transforms from the root to the leaf. Really good questions. And I think this next example I'm going to do for the arm will sort of show how that goes all the way to the root, to the root node of the hand. Sorry, not the root node, the leaf node of the hand. Let's see how it plays out. Let's move on to the hand. So we pop the matrix. So where are we now? We're conceptually back at the torso. So we're going to start drawing the arm, and it's going to be relative to the torso, right? So we can push the matrix. The pop is going to be much later. I haven't got to it yet. Translate -2, 3. Okay, -2, 3. Okay, so I guess we're sort of at the shoulder, if you will. Rotate right shoulder rotation. I think it's 0 in this case because it's not rotated. We'll come back to that in a little bit. Draw the upper arm. Okay, great. We didn't pop yet, okay? We're pushing now. We're still conceptually in the arm. So we push matrix again. It makes a copy again of where we are. And then we concatenate, translate 0, -3. What does that mean? We went down 3 units vertically. Translate 0, -3. Rotate the elbow rotation. I guess it's a small rotation in this case. And then we draw the lower arm, as you can see here. Push matrix again. You can see this every time we push the matrix, this is conceptually going into a subgroup, okay? And you can see how the transforms are concatenating. When I push this matrix from the lower arm, and then I apply translate 0, -3, I'm going from the lower arm down to the hand. I apply another transform, rotate wrist rotation. So now I'm rotating the wrist, and then we draw the hand, okay, which is down there. Then I pop a matrix, which means I'm back conceptually at the group of the lower hand. I pop a matrix again, I pop a matrix again. If you're counting, that gets me back to the torso. Yeah, why don't we rotate first and then translate? Yeah, good question. I really like that question. I think as you can see the code written here, in terms of how it's organized, I think I would just make the claim, I think it's more conceptually smooth. It's more conceptually ordered to go in the manner, in this ordering. And that will cause you to have to, kind of go down the arm. Or maybe I misunderstood the question on why translate first, then rotate. Oh, well, if you're going down the arm, then I think I wrote it this way, translate first, then rotate, okay? You have to consider the order in which you multiply these matrices mathematically, okay? And that'd be a good thing to go check. So when you write this rotate wrist rotation, what's gonna happen? It's gonna take the matrix for rotate wrist rotation, and then it's going to multiply it against the matrix that's on the stack, right? The last, the current matrix that's at the top of the stack. Is that a right multiply or a left multiply? Good thing to think about. Okay. Anyway, so you get this. Okay, pop, 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 back to the torso. And then you can draw the right arm, you draw the left leg, right leg. But what happens if you want to rotate just the arm? Okay, so this is the right hand, right lower arm. I sort of went through this. Okay. So if we want to change just the rotation on the arm now, all we have to do is change just this one location. We change this one parameter, right shoulder rotation, which changes this one matrix here, and then okay, we can rotate the arm. Okay. Scaling, I see a few questions here. I think Rishi can probably help me with some of these. Yeah, let me pick up a couple of these. Is the rotation relative to the parent frame? Is the rotation relative to the parent frame? It is, because, and I'll emphasize this again, every time we push the matrix, we push a copy right onto the stack. So we have a copy now there, but we still have the matrix on top. The current matrix. And then when I say translate 0, 5, this does not replace that top matrix with translate 0, 5. It composes after that matrix, we then do a translate 0, 5 on top of it. Which, if I say, is it left multiplication or right multiplication of the matrices? You just remember right to left, worth really thinking through those details and anchor it, okay? So convince yourself of which one it is. That's going to modify the matrix that's on the top of the stack. So all of these additional translates, rotates, they're all concatenations on top of the existing frame. Okay, I showed you a simple example there. This can be extended and is extended to all kinds of examples, very fine detailed skeletons, very multi-part sort of systems. It doesn't just have to be for one character. You can define a house, relative parts inside the house, furniture inside the house. You could then replicate that house, for example, and make copies of it at different positions on a street. You could copy and move streets around. You could array them either in lines or rows or in sort of like patterns that are more, curved, build cities this way, so on and so on and so forth. And if you want to move streets, then you might have one grouping of a lot of houses that compose a street as an example. You get the idea. Okay, so you can kind of see right away why hierarchical transforms are so ubiquitous. Yeah, there's a question about scaling. I did mention, sorry, I said that maybe that was a bit confusing before. I said, well, we can sort of think of this character as like a composed of a unit square that's sort of scaled and then sort of, drawn for each of these body elements. You can sort of think of that as like, if that were happening, of course, you could just draw a rectangle too. It's not, not that complicated. But if you thought of it as scaling a unit square, then that might happen in draw head or draw upper arm or draw lower arm. Okay. Sorry for any confusion about that. Okay. 2D transforms, 3D transforms, hierarchical transforms, and sort of how they relate to composition of transforms. A lot of stuff in modeling of worlds, okay? Transforms are for modeling. I want to switch gears now and start talking about using transforms for viewing and perspective in graphics. So let me show you a picture to remind you of the issue that I raised, sort of the intro comments that I have for this lecture. The issue is that we have these objects that are defined in 3D space. For example, here, this little baby cow is a triangle mesh, okay? And we're describing them in some kind of world. And then eventually, though, we want to draw them to the screen. And all the stuff we talked about in rasterization had to do with drawing triangles that were defined in the 2D plane, right, of the screen conceptually, and specifically 2D within the frame buffer, okay, coordinate system. So we have to have some kind of way of putting these 3D objects, into a 2D or projecting them into a 2D representation of the frame buffer. I think the cows are really cute too. Okay, so that's what we're talking about here. And obviously, like if we view the little cows from this side, we'll get one set of triangles, right, on the frame buffer. If we just rotate around the camera and look at them from behind, then, of course, we'll see the back of the head. We'll see, like just a totally different view of it. And we'll get a totally different set of triangles, 2D triangles projected into the frame buffer. Okay, so viewing is really critical for, and changes very dramatically the kinds of things that get rasterized. In order to, work out the sort of coordinate frames and the coordinate systems of all of this, I'm going to introduce a few bits of nomenclature, okay? First is camera space. We need some kind of convention for talking about where the camera is, okay, and which way it's pointed. So we're going to transform from world coordinates into something that we'll call camera space, and I'm going to define a standard camera space here. This is not universal. It's very common, this version of this definition, but there are different versions for different, gaming systems or for modeling systems. You kind of just have to know which one it is, okay, and pay attention to it to the degree that it matters. Otherwise, things might end up flipped on your screen or, or other things like that. The standard we're going to use has elements that are common to all of them. We have to define, okay, which way is pointing up, which way is to the right, and then which way is forward and back. And we're going to choose this coordinate system here where X is pointed. If you're holding the camera, X points to the right, Y points up, and then Z points backwards from the way that you're facing, as you can see drawn here. Okay, so if you, for example, were looking at, imagine holding this camera and took a picture in the world, then where are the coordinate systems? The coordinate system of this projected image. Okay, this is a real photo, but you could imagine as if it was a graphics rendering. X goes to the right, Y goes up, and then Z points out of the screen. Okay, out of the screen, away from the alpaca and towards us. So consider a camera pointing in the world at this point. Okay, so we have some kind of 3D space. We have a photographer here. Let's think of the picture that's being made by this photographer in this camera. Now, in this world, right, we have to describe where the camera is. So we can talk about the camera. By the way, this is different than camera space because standard camera space is how we're going to transform all the stuff in the real world into that camera space. And then we're going to go from camera space to put it onto the screen and, onto the frame buffer. Okay. This is sort of saying, well, relative to all the objects in the world, where's the camera? Okay. So subtle difference there, but very important. This camera has an up vector, we'll call it U, has a view direction, we'll call it V, and then there's a position in the 3D world, right, which we call E for the eye point. So if I give you E, U, and V in world space coordinates, which means, right, so just to not to belabor the point here, but it exists somewhere in the world. So we're going to have to decide in that world, where's the origin, where's the X unit vector, Y unit vector, V, Z unit vector, all that needs to be described so that, for example, we can put all the other objects like the lake, those rocks, the two characters on the left-hand side, we have to put them into that world in that coordinate system. In the same coordinate system, world coordinate system, we're going to say EUV, that's where the camera is, okay? If I give you EUV in those world space coordinates, what we want is an output transform matrix that goes from world space, all the objects are going to be described in world space, go from that world space coordinates to standard camera space, which I defined on the previous slide, okay? You can think of this as a look at transform, okay? How can we derive this matrix? It turns out that we can just apply the coordinate frame transform that we've been talking about, but we just need to do it a little carefully and make sure we get it going in the right direction and not inverted. So let's think of the inverse first. I'll go back and look very carefully at this definition. The look at transform wants to go from world space to camera space, okay? The coordinate frame transform that we've talked about goes from object space to world space, okay? From object coordinates to world coordinates. So the inverse of the look at transform, going the opposite direction to where we want the transform to go, is the coordinate frame transform using EUVR. Okay, and it's E, the location of the coordinate system, the location of the camera is EX, EY, EZ, it goes here, and those other three kind of go like this. Why is there a negative sign here? It has to do with the definition of this viewing vector. Here I define the viewing vector as the camera, which way the camera is pointing in the world, but our standard coordinate system here has Z-axis pointing backwards, okay? So that's why there's a negative sign here. It comes from those two definitions there, geometrically. And I explain why it's the inverse matrix. So the look at world to camera transform matrix is just this coordinate frame transform inverted. Which it turns out you can write down in closed form this way, okay? It's maybe a little surprising that can be done. As you know, it's not always easy to write down what the inverse of a matrix is, and this is a 4x4 matrix, but it's pretty conceptually easy because this can be thought of as a rotation in 3D space, and then and maybe a scaling, and then a translation. So we can actually write it as a inverse translation matrix, and then a composition of all of these, like a permutation of these coordinate axes as shown here. You can multiply all this out and convince yourself that this actually is the inverse matrix. Again, not a bad exercise to do. The last thing I want to say for today, and we'll pick up next time talking about perspective, but the last thing is that once we get into camera space, so we transfer all the world coordinates into camera space coordinates, where's the frame buffer again? How does this work? So then conceptually, we can think about collapsing down onto the image plane. One way to do that is to just delete Z, just ignore Z, okay, and just have all of those triangles, the XY coordinates, end up being the coordinates in the frame buffer. This would be called like a parallel projection or an orthographic projection. And it's used quite a lot in engineering fields, for example, in engineering drawings for doing things like architectural elevations or cross sections, things like that. Okay. But this is not the whole story. Definitely not the whole story. In fact, it's not even the most common story. The place we'll pick up next time has to do with the way that the most common way we look at stuff projected to the screen, which involves a bit more work that we can talk about, has to do with perspective. This is not the same as just projecting after taking all of this 3D world and putting it into camera space. It's not just deleting the Z coordinate. We're having to do more calculations, specific calculations, in order to create this sense of foreshortening of further things in the world looking smaller to achieve this linear perspective. Okay, so we'll pick up there next time.